In the last lesson, I reviewed with you some of the ideas we learned last year about capacitors. We saw that a capacitor could store charge, store energy, and create an electric field. We saw that the capacitor got better when it had more area and less distance. We saw that the charges rushed onto the top plate and then repelled the charges from the negative plate, making it positive, pulling more electrons to the top plate. We saw a bigger area let us store more charge, and we saw a smaller distance let us store more charge. We saw the role that the insulator played in making for a better capacitor. We saw the formula on how to calculate capacitance. That is determined again by area, distance, and insulator. We then found out how much charge was on the capacitor, how much energy was on the capacitor, and then how strong the electric field was in between the plates of the capacitor. So we charge our capacitor up, and then when I view the electric field, we can see that it points from the positive plate up to the negative plate. Remember, if that electric field gets too strong, a spark will jump through your insulator. Okay, so we found the formula on how to get the field. What I'd like to talk to you about today is combining multiple capacitors together in either series or parallel. Why would you want to do this? Well, it turns out that capacitors are amazing in terms of the way that they are able to charge and recharge really quickly with high amounts of current. They could be charged and discharged many, many times, way more so and way more easy than a battery. So since capacitors usually have a very low voltage or are not able to store a heck of a lot of charge, the only way we could use these things practically is combine a bunch of them together in a bank of capacitors. So here's a bank of capacitors to increase their effectiveness. Here's another bank of capacitors. So you see it takes lots and lots of wires and a lot of know-how to make sure you're hooking them up properly. But these can become extremely useful. Things like a railgun that we're going to learn about later in the year are one of the most tremendous uses of capacitors, where we can fire a projectile at unheard of speeds based on the amount of power we're able to get out of this bank of capacitors. So again, you can see how many capacitors this guy is using, but it's extremely powerful. Here is a more industrial strength railgun development area, and you can see again, lots and lots and lots of capacitors. Cars can accelerate more rapidly than any gas engine ever developed when you power them with capacitors. Capacitors one day may take the place of all batteries because they are just so much better in a lot of different ways. The problem is getting a lot of energy and charge stored is not possible on a single capacitor. So we got to know how to hook these up properly so that we can increase their efficiency. All right, so you can see here, lots of capacitors hooked together to form a bank of capacitors. So let's see how it's going to work. Let's start with a single capacitor hooked to a battery. The blue bar indicates how much charge is stored on the capacitor. Again, that stored charge is on the negative plate because the capacitor itself is neutral. It has one negative plate and one positive plate. This time, instead of changing anything about the capacitor, we're going to add capacitors together. So you can see I added a second and then a third capacitor in series. So for this one, draw it out and put down capacitors in series. And you'd think, well, I got 3 capacitors, that's 3 times better than a single capacitor. But that turns out to be wrong. If you were watching this bar, you'll notice that the charge stored is actually less than it was originally. So adding more capacitors actually made the situation worse in terms of charge being stored. Why is that? Well, I hope you realize that the charge comes out of the battery and deposits itself on the top plate. Charges then get pushed off the other plate and they go on the second capacitor. So here's the deal. The charges on the second capacitor do not come from the battery. They are simply the remnants of the charge on capacitor 1. Same thing here. These charges come from the second capacitor. So whatever charge I put here, I have the same charge here and the same charge here. And you don't add them together. Those charges are all equal to the charge that came out of the battery. So adding more capacitors does not actually let more charge come out. In fact, it lets less charge come out. Why? Because now instead of having one gap, we have to push across 3 separate gaps. So adding more capacitors in series makes things worse. It's as if you increase the distance between the plates, which we learned is not helpful if you want a lot of capacitance. In fact, to find the capacitance, for a series, you don't add them, you add the inverses. It is just like resistors were in parallel. With resistors, every time we added another resistor, we added another path and we made the net resistance go down. Here, it's series, and every time we add another capacitor, we make the capacitance in total go down. So why would you ever do this? Why would you hook capacitors up in series if it makes things worse? Well, hopefully you also remember that if you put too much electric field between the plates, a spark will jump between the plates. So every capacitor has a limit in terms of how much voltage it can handle. So if this guy can handle only 1.5 volts, by hooking 3 of them up, we're now able to get a total of 4.5 volts without creating a spark. So the advantage to hooking them up in series is that it would allow us to have a higher total voltage than we could get on a single capacitor. The downside is it makes less total charge. Okay, so here's another one. So we start with a single capacitor. Again, look at what your storage charge looks like. And this time, we're going to hook our capacitors up in parallel. And I hope you see that this bar went up. We're now able to store more charge than we were with a single capacitor. So in parallel, more capacitors mean more stored charge. Why? Because this time, each capacitor is storing charge that originated in the battery. Each of them are going to push their charges back into the battery. So if we have charge 1, charge 2, charge 3, that is actually storing all of them. They are all unique and individual charges. So to find out how much came out of the battery, we add them all up. Notice each path only has one gap that it has to push the charges across. We did not increase the number of gaps that are going to be experienced by any single path. However, we did increase the area because now we have 3 different plates that we could store unique charges on. So hooking capacitors up in parallel increases the net area to store charges. It makes it more efficient in terms of capacitance. This time, to get the total capacitance, we literally just add them all up. Okay, so this gives us more capacitance and more charge. It will, however, limit how much voltage we can use, because if they can handle 1.5 volts, then we can only have 1.5 volts. Each of them is its own individual path, and this will not allow us to increase our voltage. Okay, so here we have 3 capacitors in series, and again, that allows us to get a higher voltage before these capacitors spark. Here we have our capacitors in parallel, and that will allow us to have more charge stored, but not a higher voltage. Okay, so what I'd like to do is I'd like to think out loud and talk about how I could use a supercapacitor that has a maximum voltage of 3 volts to act like a car battery. So if I need 12 volts, I can't use a single capacitor. I would need to hook them up in such a way that I get a total of 12 volts. So what I would do is I would hook them in series. Now no capacitor has exceeded its limit of 3 volts, but combined I have 12 total volts, and I can mimic the car battery. The problem is when I figure out how much charge is stored and how much energy is stored, when I do it for the single capacitor, I have 100 farads, 3 volts, that gives me 300 coulombs. Here, yes, I have 12 volts. However, my capacitance is not 100. It's not 400. I have to add the reciprocals, and this actually turns out to be 25 farads. So I would have a capacitance of 25 combined and a voltage of 12. This is going to turn out to give me the same charge that I had before. So even though I'm using more capacitors and I have more voltage, I'm not getting any extra charge. When I do my energy, I would have 450 joules of energy, and down here, I would actually get more energy stored than I did before. So I do get a little bit more energy, but I don't get any extra charge. Again, I hook them up in series so that I could produce a higher voltage, but I do not get a higher charge. So how could I get a higher voltage and still have a capacitance of 100 like I started with my single capacitor? So what you would actually have to do is use a whole bank. This is where we get the capacitor bank from, a whole bank of capacitors, where we hook them up. 4 in series, hooked with 4 rows of that in parallel. This would give us 12 volts. Each row is acting like 25 farads. So when I combine it all together, I just add them up since they're in parallel, and I'm back to 100 farads. So in order to produce what I want, which is high voltage and a high amount of charge, I want to hook them up in a giant bank, parallel and series, both of them at the same time. Now when I figure out how much charge is stored, I can use the 100 for the combined capacitance of that whole mess, and my voltage of 12. Okay, I now get much more charge than I had before. And when I find my energy, you'll find my energy too is off the charts compared to what I had originally. Okay, so sometimes you want series, sometimes you want parallel, and sometimes you want both.